introduced. As I said, gives back to us the sum of squared errors for a given value of phi1. For instance, if we take compute the function for a value of 0.1, this is the sum of squares. If we take the function for a value of 0, this is the sum of squares, which should be the variance of the series. Let me ignore the sum of squares of the series, because if I take sum delta t squared, I should get the same, yes. Now, we can move forward with the trial and error procedure, so we can take 0.2, and you see that the sum of squared error is decreased, 0.3, again decreased, 0.4, decreased, 0.5, decreased, 0.6, 0.7, and now you see that it started to increase again, so it's somewhere in between 0.6 and 0.7. Okay, now let's use an automatic procedure, and let's use DE optim, not just optim, because here you see that there is the code suggests the use of optim, but I already told you that it's better to use DE optim. So let me see if I have to download it or this. Okay, it was already downloaded in my PC, so I just had to put the library instruction, and it should be the same for you if you already downloaded the optim. I don't remember which is what are the required, okay, lower and upper, and then nothing else. So basically, now I can compute, I can run the optimizator like result equal DE optim as lower and upper. So lower is -1, upper is +1. Okay, done. Let me do it again because I was too quick. This is the command line. This is a command. Yes, but I just wanted to use the wide range because it is, in any case, it is not so large. So yeah, it could be, we could have used 0.6 or 0.7. So basically, if you just press, you see that you have 0.619, and basically, if you just look at the result, it doesn't say much more, I think. It gives to you the population of the 10 best parameter values, but it's, they are all the same. So basically, names, I don't remember what the names of people remember. Okay. So let's go back to our code. So we already computed the best parameter value, and now let's compute the residuals. And this is the instruction. And in this case, it was I have to change something because it's better if I put 6129, because you know I have to change the code because in the version that I cut and copied and pasted, there was still the result of the previous instruction. I changed the instruction and therefore they have to adapt it. So these are my residuals or errors. Let's now compute the autocorrelation function. And let's see how it looks. You see that it's perfect. It's completely within the blue bands. Good. Now let's move forward. First of all, now I need to introduce you another issue, which is a statistical test for normality. And I could use this one, or I could use another one. Let me try to use another one. And here, because I didn't explain to you how to apply the Kolmogorov Smirnov test, it's very simple. But let me now use another one, because it should be embedded in R. First of all, what is our aim? Is to check that the residuals, we already checked that they are not correlated, but now we have checked that they are Gaussian. So in order to do that, first of all, let's plot the density of the residuals. So you see that the density seems close to Gaussian. But of course, this is not really a very powerful test because it's difficult by eyes to say if indeed this density looks Gaussian or not. So let's try now to perform a more rigorous test. I'm trying to remember because there is a common line, in order to perform this test. I don't remember. I think it is. I'm just trying to make an attempt. Okay, here it is. Now I explain to you, the instruction is QQ norm epsilon. QQ norm is the instruction to perform the statistical test. And then this is the result. And let me explain to you what is this. So let's suppose that you have your series of epsilon. And then let's put it in ascending order. And let's compute the frequency. The cumulative frequency of non-exceedance. And you know what is. Because we already spoke about it when I introduced, I don't remember, I'm sure that we already mentioned the frequency of non-exceedance. And so you compute the frequency of non-exceedance, which is, as you know, an approximation of the probability of non-exceedance. I think, because now that I remember, sorry, I open and close a parenthesis, I think I already explained to you what is the probability test. Or yes, okay, that's fine. So let's now introduce. So basically, in the code, you see in the code how to perform the Kolmogorov-Smirnov test. And now let me introduce another test. So the Kolmogorov-Smirnov, you know how to perform it, and you have the code. So basically, there is nothing new. Instead, in this case, I'm telling you something new. So this cumulative frequency of non-exceedance is, as you know, an approximation for the probability of non-exceedance. And then I can compute the normal quantile NQ of F here. So basically, I take one number, I compute the frequency of non-exceedance, and then the quantile of that frequency of non-exceedance, the normal quantile. And let's say that I take the normal quantile from a normal probability distribution, of course, which has the same mean and same variance with respect to epsilon. So now, let's suppose that epsilon is Gaussian. If epsilon is Gaussian normal, I take for any epsilon its probability of non-exceedance, and then the inverse of the normal distribution. I should get back to the same number. If it is normal, basically, I am computing for each number the probability of non-exceedance, and then the inverse of the same probability distribution. So I should get back to the same number. This is transformation and anti-transformation. From a number which is Gaussian, I take the probability and then the inverse of the probability, which is the quantile. So I should get the same number. But only if epsilon is normal, otherwise I get to a different number. And therefore, if I make a plot of epsilon versus normal quantile, if I get a straight line, I am done. It means that epsilon is, a straight line which has a slope of, it's the 1, 1 line. 1, 1. Which has a slope of 45 degrees, which means that to any epsilon, you get back the same number. If you get a straight line, a 1, 1 line, then it means that indeed the assumption of epsilon Gaussian is satisfied. And you see there that indeed you are close to a straight line. And there is also the way, but I don't remember and I don't want to insist on this, there is a way to perform a statistical test of displacement along the 1, 1 line. I really don't care about it because we are engineers, and as engineers I think the visual result for us is more important than a quantitative test, because we can see that it's acceptable for us for the purpose of designing. Okay, fine. So the residuals are Gaussian, and therefore I am happy because the residuals are without correlation. They are Gaussian, so that's fine. I can move to generation of synthetic data. By the way, if you want a quantitative test, then there is a Kolmogorov-Smirnov, which we don't perform here. Now, in order to simulate the data, let me use a function that is embedded in R. And of course, I could simulate by starting from the generation of epsilon and applying the formulation for the autoregressive model. I could make the program by myself, but let me use in this case the function that is embedded in R. So I copy it and I paste it here. Sorry for I don't understand why. Ah, okay. This is the instruction, and let's try to understand what is. First of all, the name of the variable is just my idea, SDT data, and the function is arima.sim. Arima stands for arma plus one I in the middle, which means integrated, because this is a function that can be used to generate from whatever bigger class of models ARIMA, so we forget about the ARIMA and then we focus on the AR. Now, the first argument that we should give is the length of the simulation, which is 50 years, 365 times 50. Now we have to specify what is the model. And the model here is, given by providing the autoregressive coefficient. So one writes AR equal 0.61, I don't remember, can you please tell me, CO2? Okay. And of course, if you give a vector instead of a single number, it will generate from an AR2. If you give a vector of two numbers instead of a single number. If you just write AR equal one number, it assumes that there is only one autoregressive coefficient, and therefore that the model is an AR1. And then you have to specify what are the innovations. Innovations is, again, a synonym for error or residual. And the innovation is, as we know, a random outcome from a Gaussian distribution with mean equal to the mean of epsilon and standard deviation equal to the standard deviation of epsilon. This is the explanation of this command instruction, and you see that by just pressing enter you get the simulation done. Good. Now we have to put back the seasonal component. Let's go back to the code. This is the instruction. Done. I'm just multiplying by the seasonal standard deviation and adding back the seasonal mean. Now just for comparison, let me plot the autocorrelation function as data. This is the autocorrelation function, which looks similar to the correlation function of our observed data. Non è periodico?
No.
C'è qualche errore? Ma cosa ha messo come lag punto massimo? Perché non vorrei. Cosa ha messo lag punto max 730?
No.
Okay, so the autocorrelation function, as we said, is fine. And now we have to compute the flow duration curve with uncertainty. What does it mean with uncertainty? It means that we have to compute for each year, each simulated year, the corresponding flow duration curve, so that we get an idea of the variability, uncertainty, of flow duration curves from year to year. So let me define an array. The array is the array of the flow duration curves, and the array should have a dimension of 50 times 365. For now, I define the array by filling it with zeros. And now I have to compute the 50 flow duration curves, and this is the instruction. So I have to repeat for I between 1 and 50. And then at each year, I compute this PR3, which is the reverse of sort of the data of that year. So basically, in this instruction, look at sort. Sort means that you order the data in ascending order. Reverse, REV, means that you invert the vector, so you get it sorted from the biggest to the smaller. And what you sort at each loop are the data of the ith year. And you see that by changing I, not ith, sorry, the data of the ith year, if you change I in the loop, you basically change, if you look at the index of the data that you are getting, the index is changing with changing I, and it's changing in a way that it gets shifted 360 data forward at each time. You see I minus 1 times 365 plus 1. So think at I equal 1. I minus 1 is 0 times 365 is 0 plus 1, so you get 1. And then you have I times 365. So at the first round you get from 1 to 365. The second round you get from 366 to 730. So you get this data by advancing each time 365 positions. These data are ordered with sort in ascending order, and then the vector is reverted in descending order. And then you plug in the matrix the result with the index I. So FDC is a matrix which has the first index, in this case I, varying from 1 to 50, and the second index, which is not displayed here because it's you can avoid to display it if you want to plug in a vector. The second index is varying from 1 to 365, and then you plug in the vector PR3, which is 365 long. At this stage we can close the fourth cycle, and we have already computed our flow duration curves for each year. Now we can draw a graph. Let's draw this graph. First of all, let's plot the first flow duration curve. Which is this one. Look at how I drew this plot. I put a limit for the y-axis, for the ordinates, between 0 and the maximum of the matrix, in order to make sure that when I have the other curves, they are not going outside the range covered by the ordinates. So basically this is our result, and then I can plot all the other curves. And this is the result that you get. So basically you have an estimate of the flow duration curve with uncertainty. And you see that at the end of the code, there is written, you may check if negative values are there, and if you basically, in the simulation, it may happen, the simulated data are S data. If you look for the minimum value, you see that there is a negative value. Because, you know, the stochastic process doesn't take into account that the data are bounded by 0. So it's better if you see that there are negative values to put them equal to 0, because they have no physical meaning, negative values. So in order to impose that any negative value is equal to 0, you see here the instruction. And now if you try to recompute the minimum, is 0. Okay. And basically, I think that we can stop here. The only issue that we didn't consider was, apart from the Colmogoro's wheel of test that you can easily try and apply, we didn't consider the smoothing of the data, but even in this case, I think you can move forward by yourself.